This last section here in chapter 6 uses normal approximations for binomial distributions and to something new called p-hat distributions or proportion distributions. Okay, so we talked about a normal distribution. We've talked about a normal curve and its properties. We've talked about the standard normal distribution. And we've also talked about using sampling distributions and approximating sampling distributions with normal distributions using the central limit theorem. Here, we're going to go back to binomial distributions before visiting what's called p-hat distributions. All right, so let's consider the following question here. So the probability that a new vaccine will protect adults from cholera is known to be 0.85. This vaccine is administered to 300 adults who must enter an area where the disease is prevalent. What is the probability that more than 280 of these adults will be protected from cholera by the vaccine? So what's given in this question calls for a calculation using a binomial distribution. We've done that before, right? Our N is 300, our P is 0.85, our Q is 0.15, and the number of successes that we want is greater than 280. Now, usually, we can use a binom CDF to calculate this in this way. So because this is a greater than case, we look for the less than case and subtract it from 1. So let's actually go ahead and calculate that and see what that gives us. So 1 minus binom CDF, my trials is 300, my P is 0.85, and because we're doing a less than case, or because this is greater than, we want less than or equal to 279. So my x value in question is 279. Okay, so here's what it will look like on the calculator. Here is the value of that. That probability is pretty small, about like 0.000007%. Now, the larger our sample space is, we can also use a normal distribution to approximate the binomial distribution. Very similar to how we did the Poisson distribution. Remember, when we do a Poisson distribution to approximate the binomial, remember the criteria for that. Our sample space, our value for n had to be at least 100, and the mean of that distribution had to be less than 10. Okay, so consider a binomial distribution where you have a number of trials, number of successes, and the probability of success on a single trial, of course, with Q being the probability of failure. So if the number of trials times the probability of success, if that is greater than 5, and if the number of trials times the probability of failure is also greater than 5. Now, those don't have to be the same number. As long as each of those is greater than 5, then R has a binomial distribution that is approximated by a normal distribution with the same mean and the same standard error, the same standard deviation as a binomial distribution. And as the value of n increases, as the number of trials increases, the approximation becomes more accurate. It becomes more normal. So here's an example. Graph the binomial distributions for which the value of P is 0.25 and the value of Q is 0.75. And the number of trials is n equals 3, then 10, then 25, and then 50. If you look, so here's the first one where n is 3. So it looks very let's see, left skewed. No, right skewed. It looks very right skewed, kind of stretches out to the right. As my n increases to 10, it's still a bit right skewed, but it's starting to level out a little bit more. As we get to n equals 25 and n equals 50, we can start to see that distribution being more normal, being more bell-shaped, right? And it becomes a good normal approximation. So let's practice that here. The owner of a new apartment building must install 25 water heaters. From past experience in other apartment buildings, she knows that quick hot is a good brand. A quick hot water heater is guaranteed for 5 years only. But from the owner's past experience, she knows the probability that it will last 10 years is 0.25. Okay, so let's apply this with the context of the binomial distribution. Okay, so the probability that it will last 10 years is 0.25. So here's my P, which means my Q is 0.75. Letter A. Is a normal approximation appropriate to use in this situation? Okay, so what we're going to do is first we're going to calculate NP and NQ and see if they're both larger than 5. Well, what's N? It's 25 here. N is 25. So let's calculate NP and NQ. Remember, NP is the mean in a binomial distribution. Okay, let's not forget that. So 25 times 0.25, that's 625. And yes, this is greater than 5, so check. NQ. So 25 times 0.75, that's 18.75, which is also greater than 5. Okay, so that's also a check. So is a normal approximation appropriate to use in this situation? Yes, it is, because my NP and my NQ are both larger than 5. So if so, use a normal distribution to approximate the probability that 8 or more of the 25 heaters will last at least 10 years. Define success to mean a water heater that lasts at least 10 years. Now, the first thing we're going to do is we want to take this number and subtract 1/2 from it. There's a perfectly good reason for that, and it will be explained later. So, but let's just go ahead and work and do that first. So 8 minus 0.5, that's 7.5. So this is the value that we're going to use instead of 8. And again, I will explain why in a later slide. Okay. So we want the probability that that R is going to be greater than or equal to 7.5. Now we're going to use a normal approximation. We're going to use a normal distribution to approximate this probability. Okay, which means we need to find the we have the mean and we have the standard deviation, right? So the mean is, well, first off, we know the mean is 6.25. We've already calculated this. We need to find the standard deviation, which is the square root of NPQ. So that's the square root of, well, we've already done NP. Q is 0.75. And we'll round that to 4 decimal places like we did in the last section. So square root of 6.25 times 0.75. I get a standard deviation of 2.1651. All right, so we're going to use a normal approximation here, which means I need to find the z-score pertaining to this. Also, this is a greater than case. So what I want is, first I'm going to find the z-score. I'm going to find the less than case, and then I'm going to subtract it from 1. Okay, so my z-score, x minus the mean, or in this case, r minus the mean, divided by the standard deviation. So that's 7.5 minus the mean, 6.25, divided by the standard deviation, 2.1651. So let's go ahead and calculate that. Okay, 7.5 minus 6.25 divided by 2.1651. Rounded to 2 decimal places, I get a z-score of 0.58. And remember, this is a greater than case. So I want 1 minus the probability that my z-score is less than 0.58. So I'm going to go to my table. I'm going to look for 0.58. So here's 0.5, 0, 1, 2, 3, 4, 5, 6, 7, 8. That's 7190. 0.7190, which is 0.281. 2810. So that's my probability. Let's attempt the same problem using the formula for a binomial probability distribution with this n and this p. Okay? So, erase this real quick. We'll work that over here. Now, what I'm looking for is, back to my original problem, P of R greater than or equal to 8. That was my original problem, which means I want 1 minus P of R less than or equal to 7. And this is a binom CDF. 1 minus binom CDF with my n being 25, my p being 0.25, and my r being 7. So let's go ahead and put that into our calculator. 1 minus binom CDF, 25, 0.25, 7. Okay, here's what that's gonna look like here. I'm gonna press enter, and look what I get. I get a number that's not that much different here. 0.2735. So not that much of a difference. But then again, our value for n is pretty small. As our n gets larger, then we'll start to see these being more accurate. Now, how do the results of A and B compare? Well, once again, we have our normal approximation being a slightly bigger probability than our original binomial probability calculation here. So the error is only about 0.0075. So if I took the difference between the two, 0.2810 minus 0.2375, I get a value of 0.0075, which in practical cases, it's usually negligible, meaning that the difference really doesn't, actually, this should be a little dyslexic moment there. So because this difference is so small, it doesn't really affect much. The probability roughly remains about the same. But again, as I mentioned earlier, as your value of n gets larger and larger, these two values will become that much closer together. The approximation tends to be more accurate. Okay. So in the first part of the previous example, we subtracted 0.5 from 8 to use 7.5 as our value of r. Why did we do this? So keep in mind, when we're using a normal distribution, we're looking for the area underneath a normal curve corresponding to that value. Because we're using the normal distribution to approximate a binomial distribution, we're also looking for the area underneath the bars of a binomial distribution. Now, when we graphed a binomial distribution in section 5.3, the bars ranged from midpoint to midpoint. So r minus 0.5 to r plus 0.5. So this means that when we find its corresponding continuous normal variable, we extend that range from r minus 0.5 to r plus 0.5. This kind of adjustment is what's known as a continuity correction. So here's how to make a continuity correction. convert the discrete random variable r to the continuous variable x by doing the following. So if r is a left point, you subtract 0.5 from it. If r is a right point of that interval, you add 0.5. So if you're looking for a probability between two values of r, then when we approximate using a normal random distribution, we subtract 0.5 here and we add 0.5 here. And this is our corresponding normal random variable. And because again, we look at the differences, look at the difference between the two types of distributions that we calculated when we made that continuity correction. It's very, very small. It's barely noticeable at all. Okay. Now, normal approximations are not the only types of approximations that we covered when it comes to binomial distributions. We also did a Poisson distribution. What makes them different? What separates the normal approximation from the Poisson approximation? When we add and subtract 0.5 for the normal approximation, why didn't we do that for a Poisson approximation? Well, first, both binomial and Poisson distributions are discrete random variables, discrete random variable distributions, which means that those values of r can only take whole number values. So adding and subtracting 0.5 is not actually necessary. With the normal distribution, it is a continuous random variable. So by adding and subtracting 0.5, as you saw in that example, it actually improves the normal approximation. Because again, look at how much larger this probability was to this probability. Now it's a negligible difference, but this is a slightly improved probability. So that's why we make that continuity correction with normal approximations as opposed to Poisson approximations. Here's an example. For many years of observation, a biologist knows that the probability is only 0.65 that any given Arctic tern will survive the migration from its summer nesting area to its winter feeding grounds. A random sample of 500 Arctic terns were banded at their summer nesting area. Confirm that a normal approximation is appropriate for this situation. Use the normal approximation to find the probability that between 310 and 340 of the banded Arctic terns will survive the migration. Let R be the number of surviving terns. Okay, just wanted to make sure that there wasn't anything extra. So let's go ahead and let's confirm first that the normal approximation is appropriate. So we need to find NP and we need to find NQ and make sure that they're both larger than 5. What's our N? What's our sample? 500. So N is 500. What's our value of P? 0.65. What's our value of Q? 0.35. Okay, so we're going to do 500 times this, and then 500 times this. And let's see what we get. So 500 times 0.65, that's 325. And then 175 here. So obviously, these are very large, a lot greater than 5. We can use a normal approximation for this probability. Okay. Now, let's set up this probability. So we're looking for the probability that we have 310 less than R less than 340. That's the probability that we're looking for. This is a between case, which if we use a normal approximation for this, we can actually, we don't even have to look for a z-score. We can go straight to normal CDF for that. But first, let's make our continuity correction. We're going to subtract 0.5 here, 309.5, and we're going to add 0.5 here, 340.5. Okay, so we're going to set up our normal CDF. My lower bound is 309.5. My upper bound is 340.5. Our mean, NP, is 325. We need to find our standard deviation. So that's square root of NPQ. So we've already found NP. Square root of NP 325 times 0.35. We're going to round that to 4 decimal places. Square root of 325 times 0.35. That is 10.6654. There's my normal CDF. Let's go ahead and put that in there. Normal CDF, lower bound, 309.5. Upper bound, 340.5. Mean of 325. Standard deviation of 10.6554. And I end up with a probability of 0.8542. That's the probability that between 310 and 340 Arctic terns will survive the migration. Yeah. Now, if you wanted to find the z-scores for these, you could also. The corresponding z-scores for both of those values, larger area minus smaller area, you would get roughly the same answer. Just you'd have a difference of about 0.0012. Again, a very negligible difference when it comes to differences between the methods. Okay. All right. Now, let's say that we take that experiment, that Arctic fern experiment, and let's say that we repeated it over and over and over again with the same number of trials. And then for each time that we repeated the experiment, let's take the ratio of successes to total trials. This is what's called a sample proportion of successes. The sample proportion of successes in a repeated binomial experiment is the ratio of successes to the total number of trials in the experiment. This is given by what's called p hat. This is how we say it. P hat equals R over N. Right? Number of trials, number of successes to the total number of trials. So we can actually turn this into a distribution, right? We have the number of trials. It's got to be a fixed constant. It's got to be the same number of trials each time we repeat the experiment. And again, R is the number of successes, P is the probability of success, Q is the probability of failure. If NP is 5, and if NQ is if NP is greater than 5, and if NQ is greater than 5. Remember, we saw this earlier. Where do we see this? We saw this here, right? Because remember, we're still talking about a binomial distribution, right? The only difference is we're just repeating the same experiment multiple times. That's the only difference between the two. So anyways, where were we? Okay. If NP and NQ are each greater than 5, then that proportion, that P hat equals R over N, can be approximated by a normal random variable with the following mean and standard error. So the mean will now be the probability of success. And to calculate the standard error, the standard deviation, we take the square root of P times Q divided by N. So P times Q, divide that by N, take the square root. All right. And what does that actually tell us, right? So again, consider a number of binomial trials, right? We use the P hat to estimate P, the population probability of success on a single trial, where R is the number of successes out of the N binomial trials. To create this distribution, we have to repeat the same experiment, the same N binomial trials conducted to determine individual sample statistics P hat. And fortunately, we can use math to obtain the following. So if NP and NQ are both greater than 5, then the P hat distribution is approximately normal, which means we can use the standard normal table. We can use normal CDF if we need to. The mean is going to be the probability of success. And the standard error is, again, take P times Q, divide that by N, find the square root of that. All right, let's look at this example here. The annual crime rate in Capitol Hill neighborhood of Denver is 111 victims per 1,000 residents. That means that 111 out of 1,000 residents have been the victim of at least one crime. Let's stop right there. There's our value of P, 111 out of 1,000. 111 out of 1,000, which is 0.111. These crimes range from relatively minor crimes, stolen hubcaps, purse snatching, to major crimes like murder. The Arms is an apartment building in this neighborhood that has 50 year-round residents. Suppose we view each of the n equals 50 residents as a binomial trial. The random variable r, which takes on values from 0 to 50, represents the number of victims of at least one crime in the next year. Here's the question. What is the population probability P that a resident in the Capitol Hill area will be the victim of a crime next year? We've already calculated that. What is the probability Q that a resident will not be a victim? So Q is the complement of that, which is 0.889. Part B. Consider the random variable P hat equals R over N equals R over 50. Because remember, 50 is the value of N. Can we approximate P hat with a normal distribution? Okay, so again, we need to calculate in P, we need to calculate in Q, and see if they're both larger than 5. Okay, so N is 50 times 0.111. Oops, 50 times 0.889. So let's calculate each of those. So 50 times 0.111. I get a value of 5.55, which is larger than 5. So that's check. Now I do the same thing, but for Q. That's 44.45, which again is greater than 5. Check. So can we approximate? Yes. NP is greater than 5, and NQ is greater than 5. What are the mean and standard error for the P hat distribution? So again, for a P hat distribution, the mean of that is P, which is 0.111. What is the standard error? What is the standard error? So we got to take the square root of PQ over N, which is the square root of 0.111 times 0.889, and divide that by 50 and take the square root of that. We're going to calculate this and round it to 4 decimal places. So 0.111 times 0.889. We're going to divide that by 50, and we're going to take the square root of that number. And I end up with a standard deviation of 0.0444. There's my mean. There's my standard deviation.